Right, starting the recording. Okay, so why would you consider Cambridge? So, Cambridge provides a world-class education. You're surrounded by like-minded individuals who love their subjects. They want to collaborate and develop their ideas as a team. And in this setup, you'll be able to develop your own ideas. You'll be able to develop your own education and learn mathematics at an incredibly high level. You have a brilliant structure from the Faculty of Mathematics, Centre of Mathematics, Natural Sciences, and you're taught by some of the best mathematicians in the world. We're also supported by plenty of student services. We have a brilliant wellbeing team at the Centre of Cambridge, as well as in the college. And we also have a brilliant careers advice team. So if you're looking to go into different jobs in the future, we also have plenty of fulfilling things to do in your spare time. So we have a brilliant societies, brilliant student union, with lots of extracurriculars to fill up your spare time outside of learning mathematics. And as we can see in this infographic here, we also have the highest employability in the UK for universities. So what does it mean to be a collegiate university? So Cambridge is a collegiate university, meaning it is made up of 31 constituent colleges. All of these colleges admit students and they're responsible for the academic and pastoral care of each of its students, whereas the university owns the faculties and the buildings that are not themselves colleges, helps organise the course content and as well as the exams at the end of the year. It sets the marks and the examinations, and at the end of your degree, it's the university that will award you it. This means that in purpose, a lot of the teaching is very similar at each of the colleges because it's the faculty and it's the university that provides the teaching. Whereas the minor differences between the colleges come from the small group teaching. So your colleges will provide supervisions for you. In fact, Anthony Ashton was a supervisor for me in my first year for plenty of the applied content. And that's what the role of the university and colleges provide. And we are Homerton. So we're Homerton College based in the south of Cambridge. We combine old and new. What does that mean? It means that we have plenty of old traditions, such as formal halls, plenty of old buildings, such as the wonderful Cavendish building that is seen opposite us with a brilliant old hall. And we also have plenty of new facilities. We've got brilliant ensuite accommodation for all freshers, all undergraduates. And we have a multi-million-pound AstroTurf football pitch, as well as a college gym and a state-of-the-art library with plenty of education books. We have a large and diverse college, a community built up of people from many different backgrounds, studying many different courses. You'll have plenty of interesting conversations with people from different degrees, and you'll learn a lot of different ideas and techniques from them. We're committed to making a positive impact on the world. What does that mean? It means that when you come out of your degree, you will want to change the world. You will want to make a difference. You might not want to, you might want to land yourself a cushy job now because you've got a master's degree, but at the end of the day, we will make it so that you can actually make a difference and you can learn the skills that will change the world as we know it. We also have a brilliant world-leading development program known as the Changemakers. And a little bit of history behind Homerton. We are the newest college. In fact, founded in 2010. We opened to all courses. Before then, we were just an educational college offering the PGCE. And thinking about the kind of groundedness of the people that live here, this is Lord Simon Woolley, our principal, who everyone calls Simon because he's just a friendly guy that you will see about college. He's not a lord to us at the college. because he is just Simon. He will often play table tennis with you and chill with you in the evenings. And we also have plenty of financial support. So if you apply to student finance, you will be eligible for the Cambridge bursary, as well as plenty of scholarships and grants to help you throughout your studies. We also have a music and travel grant. So if you want to pick up an instrument or carry on with a instrument at a high level, but you need the funding to be able to play this instrument, then we can help support you in that. If, for instance, you want to go to an area of the world that has a particularly interesting mathematical history behind it, you might be able to secure yourself a travel grant. That means that you can go and visit that area. Say, for instance, you landed yourself an internship in London, which can be quite an expensive place to live. We can help you relocate there the time that you have your internship and make that internship possible for you. We also have student representation awards for people that really excel past their university level, that represent Homerton and the ideas that we support. And when times get tough and you unfortunately don't have the funds for to carry on with everyday life, we have a college hardship fund to help you with that. We also have plenty of support for young carers and care experienced students that may not have the funds from guardians or parents. And here is the application process. So you'll start off choosing your course. Hopefully today you'll come away thinking you're going to be doing mathematics. You can choose your college or make an open application. An open application means that you are randomly assigned a college, and you then will be applying to that college once you have been assigned it. You check for any admissions tests. For mathematics, there is now an admissions test, which is different to when I applied. You will now have to complete the TMUA, and the sign up for TMUA is the 28th of September. Please do not forget to sign up for this admissions test before you apply on the 15th of October, because we will need you to complete this admissions test during your application. You will be automatically rejected if you do not complete this test. And you will need to complete the additional forms, such as the My Cambridge application, which gives us some extra information about yourself during the application process, and submit any written work or take an admissions assessment. So in this period, you will do your TMUA before your interview. Now, if you excel with your application, you'll be invited to interview, where you may have a maths question, such as the one that Anthony is about to talk to you about in this next section. And hopefully, if you do well, you'll come back with a positive decision in January with an offer condition. So this gives the outline of the application process to mathematics. And there's also a sneaky ninth step. So as well as sitting your A-levels, you will also have to take the STEP, the sixth term examination paper. This is usually taken just after your A-levels, if you sit them at the end of the summer in June, and we will give you an offer based off this STEP condition as well. There are plenty of resources as well as for STEP support. If you look at the maths faculty website, there is plenty of teaching, as well as what I would recommend is Stephen Sitglass's book, Advanced Problems, an incredible book that goes through and breaks down lots of different STEP papers, STEP questions for you to do. I would very much recommend that you attempt the problem first and then see how he completes it, to make sure that you're getting the most out of the problem and actively thinking about the problem and not just reading his solutions. So that concludes my part of the talk on Homerton and why you should apply here. But importantly, please apply to Cambridge as a whole. You don't just have to apply to Homerton. We as Cambridge would love to have you study mathematics here, and hopefully Anthony will do a good job of convincing you why the maths course is so interesting.
No pressure there then. Thank you, Alex. So let me see if I can just, by the wonders of technology, share my screen. So Alex, is that coming through loud and clear?
That is, yes.
Excellent. So, yeah, second introduction, just to remind you, yes, so I'm Anthony Ashton. I'm one of 2 directors of studies in mathematics at Homerton. So if you were to come and join us, you'd see an awful lot of me and the other director of studies, who's Professor Simon Wadsley. So, right, what I thought I'd talk to you about is, first of all, some general things about maths at college, and then wider things, maths at the university. And then I want to do what I hope you're all really interested in. We'll do some maths puzzles. We'll look over some interesting mathematical results. And at the end of that, we'll do a maths interview question. It's actually a question that I used many years ago. Unfortunately, I won't be using it in December 2026, so don't get your hopes up, but I hope it's an interesting exercise into the whole debacle. So onwards and upwards. Can I get this thing to... There we go. So mathematics at Homerton. What's it like to do mathematics at Homerton in particular? So there it is, beautiful college. So it's a wonderful place to work, wonderful environment. It's very conducive to getting educational work done. The facts. These aren't terribly interesting, but they are important. So every year we admit about 10 undergraduates. So if you be entered into our cohort, you'd have 9 other people doing the same course in that particular year. And it's a great place to make friends. You have to remember that when you go to university, you kind of drop all this competitiveness. There's no point trying to say, well, I want to beat the 9 other people in my cohort. What happens is you start talking to each other over lunch. When one person isn't very good at analysis, perhaps another person isn't very good at dynamics, they have a chat, they share their understanding and their knowledge, and they both benefit from it. So it's not a zero-sum game, to put it in mathematical terms. So what are the entry requirements? Well, 2 A stars in maths and further maths, and an A in something else. Often people do something like physics, but that's not mandatory. Plus this 1-1 in step 2 and 3. Now, I have to add a caveat there. It is not the case that every single person that's admitted to Homerton to read mathematics gets precisely 1-1 or above in step 2 and 3. You see, the wonderful thing about the step exams is that we're able to review your scripts, and I can see exactly where you've lost marks. And if I can see, oh, this person's been very, very unlucky, they've lost a couple of marks here, or they carried a sign error through over there and they lost 3 marks, and that meant they had, I don't know, 1-2 instead of 1-1. I can see that, and I can make an informed judgment. So whilst the offer is 1-1, it is the case that sometimes people are admitted with a lesser score. We interview the vast majority of people who apply, which is good. We like to meet people who like to do mathematics. There is a maths with physics option. So if you're one of these people who like to do maths, but perhaps you've got a mind to doing maths for the purpose of solving problems in physics, that is an option. But what we tend to find is the people who take that option, that means that you do effectively 3/4 of the mathematical tripos in your first year and 1/4 of the physical Natski tripos. What we tend to find is when the people have done that first year, they flip over to maths. So it's not that you can't do physics at the end of the first year, but it's usually the case that people choose maths. Because if you go down the maths route, you can still do lots of mathematical physics, things like electrodynamics, general relativity, quantum mechanics. You can do all those things within the mathematical tripos. Right, this next bit, the majority of first and second year supervisions are conducted in college, in Homerton. So what's a supervision? Well, when you go along to a lecture, so in your first year, you have 8 lecture courses, and each of them are 24 lectures long. What the lecturer will do is give out what's called an example sheet every 6 lectures. The example sheet is a bunch of problems that is used to test your understanding of the material in those 6 lectures. Now, some of those problems, or indeed all of them, are challenging. Some of them are exceptionally challenging, and very few students, if any, manage to do them all. And so that means you might want to have a conversation with an academic, someone like myself, sit down in my office and go through the problems in that example sheet, and particularly figure out how to do those problems that you couldn't quite get your head around. It's also a great place to consolidate your understanding. You might come into my office and say, well, you know what, just before we get started, would you mind explaining to me this orbit stabilizer theorem? I just can't get my head around it. And then we might spend 10 minutes talking about the orbit stabilizer theorem and then move on to something else. So the supervisions are an integral part of the education system at Cambridge. And the fact that you get most of your first and second year supervisions in Homerton is a huge boon, because otherwise we might have to send you out to a different college. You might have to go to the other side of Cambridge to do an analysis and topology supervision. No one wants to do that. Far better to have supervisors based in your college that can cover far more of the material. So this is a great feature of mathematics at Homerton. And finally, this last one, we've been doing this for the past, oh, I'm getting old now. It's probably about 7 years. It's a long time. This pre-sessional course, what we do is we invite our new 1A students to come up a week or so before term starts. And we give you a little kind of what I'd call top-up course in mathematics. Because our students have come from all over the world, you've all got slightly different mathematical backgrounds. So we do this 3-day course in conjunction with Gonville and Caius College and with Girton College. And we effectively give you an opportunity to top up your mathematical knowledge, maybe give you a taster of the kind of mathematics you're going to see in the first week or so of lectures. So there you go. There's some of the basics. Now, what do you learn? This is the fun stuff. Well, you learn a lot. Here is a big list of courses. So you can see some things that are very much on the pure side of mathematics, so functional analysis, Riemann surfaces, algebraic topology. But if you keep going through that list, you'll also see some things that are like physics. There's things like cosmology, aeronautics, string theory. They're the people that think there are 26 dimensions, right? You could do all these things within the mathematical tripos. I would say in terms of spread, in terms of different directions of knowledge that you can take, it has the widest breadth of material in any course on planet Earth. That is a big claim, but I dare you to find a mathematics course that has more material than, let's say, in part 3 of the mathematical tripos. So there's absolutely masses of material in the tripos. No one gets anywhere near covering all of it. You kind of choose your route and specialize in a given area. But what I thought I'd do is I might pick out some really interesting bits from all these different topics and talk to you about them. So you can look forward to the kind of mathematics you do whilst at Cambridge. So you might have heard of this one, Buffon's needle. So this particular problem is covered in a first-year course. It's 1A probability. And if you know something about continuous random variables, you might be able to do this problem yourself. So let me explain the problem. So the problem of Buffon's needle is you're meant to have, let's say, a piece of paper, a very large piece of paper that has horizontal lines drawn on it that are, let's say, 1 centimetre apart. And you drop on this lined piece of paper a needle that is 1 centimetre long. And the question is, what is the probability that if you just randomly drop this needle, it intersects one of these horizontal lines? So I hope you can see from this picture what that means. The circled needles, that these red lines are meant to be needles, the circled needles are the ones where there is crossing of a horizontal line, whereas the non-circled ones, you can see they don't cross the horizontal line. So using some ideas from 1A probability, we can show that the probability that a needle crosses one of those horizontal lines when you drop it is exactly 2 divided by pi, so approximately 2/3. Now, that's all well and good, but this isn't why Buffon got his name to this problem. See, Buffon wanted to approximate pi to, let's say, 50 decimal places. And because this probability has pi popping up naturally in it, it gives us a natural way to approximate pi by randomly dropping needles on some lined pieces of paper. And why is that? Well, if you think of your intuitive notion of probability, if we were to do this experiment a whole bunch of times, we expect the probability that a needle crosses a horizontal line to be approximately the number of times the needle did cross the line divided by the total number of times we performed the experiment. In the same sense that when you say the probability of flipping a fair coin and getting a heads is a half, intuitively what that means is if I were to flip that fair coin 1 billion times, then about half of those 1 billion times you'd get exactly a head. So what's interesting about this, though, because we've got 2 over pi has to be approximately that ratio on the right-hand side, we can rearrange things and get pi to be equal to this other ratio, 2 times number of needles in total divided by the number of times the needles crossed the line. And you can start running this experiment, because presumably the more and more experiments I do, if I put the relevant numbers into that formula, I'll get a better and better approximation for pi. And so I didn't have much to do this morning, so I ran some experiments. So number of times I dropped the needle, so I started with 7, and then 100, and then 1100, and 11,100, and so on and so forth. And then I recorded the number of times a needle crossed the line when I dropped the needle on that horizontal lined piece of paper. And you can see what that ratio starts approaching. So initially, and this is actually the picture from that previous slide, I dropped 7 needles, only 4 of them crossed a line. So my approximation for pi in this case was 7 times 2 divided by 4. That's exactly 3.5. So that's not too far off pi. But can you see by the time I've got down to the bottom, I think the bottom is 1,111,100. When I've done that many experiments, you see the approximation to pi became 3.142. That's actually pretty good. And you might ask yourself, well, could you keep on doing this and perhaps get 50 decimal approximations to pi? Well, the answer is yes. With probability 1, you can get as many decimal places of pi as you want. The problem is it might take you 100,000 lifetimes to perform enough experiments. So it's not a good way to approximate pi, but it can be done. So that's Buffon's needle. And I fibbed a bit then. I didn't actually perform these experiments myself. I am slightly busier than that. But if you want to perform these experiments virtually, then you can go along to this website and you can basically run the simulation. So it's a nice exercise in elementary probability theory. Okay, Fermat's principle. I'm sure you've heard of Fermat's last theorem. So Fermat was, in fact, a lawyer. He did maths in his spare time, but he was very, very good at it. And one of the things he came up with is Fermat's principle. So Fermat's principle, here's the complicated looking version. Don't worry if you don't understand some of the notation here. It says that light travels in such a way so it effectively minimizes its time of flight between source and target. So if my lamp is emitting some light now and it's eventually going to hit the wall behind me, the path of light will be such that its time of travel is minimized. And this has been experimentally confirmed. So it's amazing that Fermat had this principle. And you might think, well, surely that just means that light travels in straight lines. Not quite true. So light, first of all, if it goes through different mediums, it might go at different speeds. But also, air temperature affects how quickly light can travel. So, for example, if it was very, very hot near the surface of the floor, then the light might first go down to the surface of the floor, go along there where the air is warm and the light can travel fastest, and then go up to the wall later. So it doesn't have to be a straight line. So I claim this wonderful Fermat's principle, more of mathematical physics than mathematics. I claim that this tells us why mirages work. So if you haven't seen a mirage, let me give an artist's impression of a mirage. So if you're out in the desert, you've heard of this kind of legend before. You're out in the desert, you're very thirsty, you look out in the distance and you can see a tree. But beneath the tree, it looks like you can see a reflection of that tree in the ground. And your brain processes that and says, well, there must be a pool of water there, because of course the tree can't grow directly into the ground. It must be a reflection of the tree from some water. And of course, the person in the desert goes over to the tree hoping to find a pool of water, and it's not there. Of course, this is Fermat's principle in action. So you can see these paths that I've drawn. The source of the light is B. The target of the light is A, so the light is going from B to A. And if it just went along a straight line, you see the person in the desert would just see the tree straight in front. But because some of the light doesn't travel along that path, it actually goes down to the desert floor where the air is warmer and then goes up towards the target A. You can see that from the position of that person, it looks like the tree is coming from the ground. So that is, in fact, Fermat's principle. Another example of Fermat's principle, if you ever, like me, and you're a kid at primary school, and on a hot day, you put your head down to the tarmac, you see the shimmering of the light. Well, that was because lots of light was coming down to where the tarmac was, because that's where the air was warmest, so it could travel quickest. And then it was flying away. And that's what gave it that distortion. So Fermat's principle, you learn all about that in a second year course, 1B variational principles. Okay, this is much more advanced. This is from an area of maths called geometric measure theory. This is quite specialist, but it's also quite remarkable. This is going to be very counterintuitive, but I promise you this is correct. And so I'm going to explain to you the Banach-Tarski theorem. Some people call this the Banach-Tarski paradox, but it's not a paradox. It is a statement that is true. And here is the statement. It is possible to take a ball of radius 1, a mathematical ball, and that's, it's something in R3. If R3 has coordinates x, y, and z, it's the set of points that have x squared plus y squared plus z squared less than or equal to 1. So you've got this ball, and I claim that I can split this ball up into 7 very weird pieces. And from these 7 weird pieces, I can actually construct 2 new balls of radius 1. And this seems bizarre. And often what people say is it's not possible because, over here you've got a volume of whatever it would be, 4 pi over 3. Whereas when you've built these 2 new balls of radius 1, well, that would give a total volume of 2 times 4 pi over 3, so 8 pi over 3. Well, the problem is you're using a concept of volume. You see, in this clever splitting up of the ball, what Banach and Tarski did was split it up into these 7 bits. But these individual 7 bits are so complex, it doesn't make sense to measure their volume. It's impossible to say that those 7 bits that they're broken up into has any sense of volume at all. And because of that, it means that you could do weird things with them. And so if you do enough what's called analysis in the mathematical tripos, you can actually prove this theorem is true. I promise you it's absolutely true. It's counterintuitive, but this isn't the world of physics here. This is the world of mathematics where we can get away with an awful lot more. So that's the Banach-Tarski theorem. Right, duck versus speedboat. No doubt all of you know about this this competition that's been going head-to-head, ducks against speedboats throughout the world for centuries now on the world's Great Lakes. What is this competition, if you haven't heard of it? Well, you'll recognise when you see a duck swimming in a lake and when you see a speedboat flying along in a lake, they both produce a wake, right? This kind of pattern of water that spreads out in kind of a cone shape behind them and parallel to their direction of travel. Well, the competition between the duck and the speedboat is who can make the bigger wake. So you see here the angle of that kind of cone. I've denoted alpha for the speedboat and beta for the duck. The question is, which is going to be bigger? Will the speedboat create a wider wake than the duck? Or will the duck create a wider wake than the speedboat? So just in your head now, give yourself 5 seconds and come up with what you think is a good argument to why, let's say, the speedboat wins or why the duck wins. So 5, 4, 3, 2, 1. Yes. Commit to that answer. Every single one of you are wrong. Because in fact, alpha and beta are the same. That was a cruel trick, but it is actually the fact that these two will always produce the same wake. Doesn't matter how fast they go, shape of the speedboat, it's always going to be the same semi-angle in that wake. And if you want to prove that, this was actually proved by a very famous mathematician, Lord Kelvin, in the 19th century. But you go ahead and prove that in a 3rd year course called Waves. And in particular, this is to do with some shallow water wave theory. So there you go. You learn about that wonderful competition between ducks and speedboats. Okay, that's enough kind of highlights from the mathematical tripos. Let me tell you about the interview process. So what I would personally like to see at interview. So you have to have a genuine interest in the subject. If you're going to study nothing but mathematics for 3, 4, 25 years, whatever it is, you really have to enjoy it. Otherwise, it will get old very, very quickly. So I want to see that you're interested in the subject material. I hope this next one's obvious. I want to know that you've got a good grasp of your A-level material or equivalent. If you tell me that you've done some calculus in school and you know how to differentiate things, well, I probably expect you to be able to differentiate things like x squared quite easily. Logical thinking and the ability to produce sound arguments. So this is where we start leaving the realm of high school mathematics and drifting towards university mathematics. Something that I don't think is emphasized enough. Mathematics is actually about communication. You see, it's no good being brilliant and figuring out the solution to all the world's problems. If you can't communicate to a third party why that is the solution and not some other, then you're useless. And as mathematicians, it's our job to convince people, sometimes other mathematicians, that we have an argument that demonstrates the veracity of some claim, demonstrates the truthfulness of some statement. So because mathematics is about communication, I want to see you communicate your ideas clearly and produce sound, well thought out arguments. And you can get better at that with practice. So when you're, let's say, sitting across the table with your friends or family and you discuss a mathematical puzzle, that used to happen all the time in my family. It's not really true. But if you've come up with a solution, explain to them why it's the solution. Even if you've got non-specialist mathematicians there, see if you can explain why yours is the correct solution. That's a great talent to build. And it makes the interview a much easier process if you've tried it a few times before. This final one, take on new ideas and use them in unfamiliar settings. This is intensely important because that's what we do in the mathematical tripos. When you're in a lecture, the lecturer will go, here is an idea. Actually, the idea is going to be even bigger than that. We're going to develop a theorem. We're then going to prove a theorem using a new idea. And if you're in the audience, you're expected to absorb that new idea. And even if you can't absorb it exactly there and then, at least be able to go off to your room or the library later in the day or later in the week and try and absorb that new idea. So if I give you some new ideas in the interview, I want to see if you can kind of use those ideas in perhaps unfamiliar settings. Okay, what actually happens in the interview? So first of all, they're good fun. I know there are all these scare stories about interviews on the internet, but look, if you enjoy maths, it's effectively an opportunity to chat maths with someone like me. I really enjoy chatting about maths. We'll talk about fun puzzles. The puzzles are interesting. You get a chance to show off your mathematical knowledge. And look, if you get stuck, it's absolutely no big deal. We're effectively there to help. We're kind of like your tag team partner. If you get stuck on something, we jump in and kind of give a small hint. And the purpose is to go through the interview. We're effectively solving problems together. But it's not at all intimidating. I certainly hope it's not intimidating. And if you really like maths, I think it'd be quite good fun. Next, what makes things in my life easier? Oh, the list could be made so long, but we've only got so much time. So don't stare into outer space for long periods. One of the problems with all you guys is you're all so clever, right? When I ask a question, often I have candidates who jump into, maybe it's a question about how big can I make some quantity? And the candidate might go, calculus, because sometimes I get maximum and minimum using calculus. Maybe I could use calculus. And then they go, again, all in their heads, they say, oh, no, hold on. This is a problem about kind of a discrete set of objects. And calculus is kind of about continuous things. So I don't suppose I can use calculus for this kind of discrete problem. Oh, no, I won't say anything about that. That's not what you want to do. You had two great thoughts there. First of all, you said calculus because you've maximized and minimized things using calculus. That's brilliant. That's a big tick on my piece of paper. So yes, this person understands you can maximize things using calculus. But then even more points, because you then realized that calculus would not be appropriate for this discrete problem where we've perhaps got some finite set of numbers and I'm trying to, let's say, maximize the product of something. So please explain what you're thinking in the interview. Don't just stare off into my office wall. Tell us what you're thinking. Well, that I think goes with what I've just said. This is a big one. If you're not familiar with something, let us know. This isn't a kind of test. It's not a case of if we use some mathematical word that you haven't heard before, please just say so. Or let's say we did ask you about calculus and you haven't yet covered calculus in school, not a problem. I've got effectively an infinite sized pile of maths problems. We'll simply do another one. So if we talk about something you're not familiar with, just say it's absolutely fine and we'll move on to something else. But you can see so much of this is about communication. So I hope if you take nothing else from this, please remember communication is very important. Okay, so here we're going to go on to something else. I'm going to go through an interview question with you. So if I stop this sharing, and Alex, are we able to pin the other piece of paper? Perfect. Okay.
Yeah. Just
So,
before we start, can we just make sure that everyone else can see that pretty easily? Can you
oh
raise your
yes,
hand
absolutely.
quickly?
Are you able to give a thumbs up in the?
Easy. Brilliant. Just let us know if
Yeah,
you're really struggling.
perfect. Yeah, I'm sorry, the lighting isn't great. Hopefully you can make out. I will also read any words that are on these pieces of paper to help. Okay, so you've just walked into my office. Hello, how are you? How's the journey? Oh, isn't the weather awful? Right, let's do some mathematics. And I will casually slide this piece of paper perhaps over my coffee table, and I'll say, right, I'm going to make a grand claim. I claim that if you take this 2 by 2 square, and if I put 5 dots, 1, 2, 3, 4, 5, in this 2 by 2 square, then I'll always be able to find two of them within a distance of root 2 of each other. That is to say, no matter how you arrange your 5 dots in this 2 by 2 square, my claim is that I'll always be able to find 2 dots that are within root 2 of each other. And so I'll start the question off with that. Now, I never expect anyone to go, oh, I know the answer and write it down. Never happens. Don't expect it to, oh, someone's seen the pigeonhole principle before. Well done. So if the person says, well, maybe I'm a bit skeptical. Maybe I'm not sure you can do that. So I say, well, you know what? We've only just met. There's no reason for you to trust me. Maybe I'm lying. Maybe my claim is false. And if my claim is false, then I'd say, well, can you negate that statement? If the claim is false, what would it mean? Well, it would mean then that there is an arrangement of dots so that no two dots are within root 2 of each other. That's to say the dots are so spread out, I can't find two dots that are within root 2 of each other. And I say, okay, that's a great point. Okay, well, can you give me your best guess? What's your best configuration of 5 dots so that you would hope that they're the most spread out? And 99 times out of 100, it's this. The student will go, well, I think I'd probably put one there, 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 there. That's 4. And then I'll put my final one right in the middle. And the student goes, oh, I'm very pleased with myself. I think I've won. I don't feel it doesn't look like any of those within root 2 of each other. And then, of course, I say, well, okay, well, let's slow down a bit here. What is this one? What is that length there? What's the distance between those two dots? And then the student would normally say, well, okay, well, I've seen this Pythagoras thing before. And I say, that distance there is 1. This distance there is 1. Because we said we put this right in the center. So it's exactly 1 unit up and 1 unit across. And then if that's the case, well, we know what the length of this is. It's going to be the square root of 1 squared plus 1 squared. That's the same as root 2. So in this particular configuration, I have actually got dots that are within root 2 of one another. So at least for this configuration, my claim is true. And so, okay, I'll let you into the secret. Now I'll tell the student, in fact, the claim is true. But what we're going to do together is we're going to try and solve it together. So let's see if we can try and solve it together. And what I do is I give a hint. I let the student think for a little bit. But if you've never seen this kind of thing before, this is really, really quite a clever idea. I say to the student, well, look, does it help at all if I draw on some kind of imaginary lines going right down the middle there and right across the middle there? So I've split my 2 by 2 square into 4 smaller 1 by 1 squares. Does this help us at all? And the student will start thinking now, this is still very difficult, so I'm not expecting kind of like perfect solutions or anything. The student think for a while and says, right, okay, well, look, I've got 1, 2, 3, 4 boxes. And effectively, by putting 5 dots into this big square, I've got to distribute 5 dots amongst these 4 boxes. Now, I'll be nodding enthusiastically here, saying, exactly, yes. So we've got 4 boxes, 5 dots. What does that mean? And the student will say, well, I guess if I've got 5 dots and 4 boxes, then I can't avoid having, well, 2 or more dots in one of those smaller boxes, right? Because if you try to avoid that, you'd say, well, I can only put 1 in there, 1 in there, 1 in there, and 1 in there, but that would only be 4 dots. Of course, there'd be nowhere to put the 5th one. So the student comes to the conclusion that there must be one of these smaller boxes that has 2 or more dots in it. You know what? Without loss of generality, let's put them both in here. And then the student starts to think, and then I can sometimes see the eureka moment happen. Because what can we see about 2 dots that happen to be in this same 1 by 1 square? Well, within this 1 by 1 square, what's the most I could possibly separate those 2 dots by? Well, that would be if I put 1 dot at one vertex and 1 dot at another vertex. So that's the most I could possibly spread 2 dots out if they're in the same smaller square. And of course, what is this distance? Well, again, just by Pythagoras, that distance is square root of 2. And so there we go. That's actually the conclusion of our theorem. But I wouldn't be happy in just leaving it there. Because remember, I said that communication was very important. I want to know that the student has understood the logical path that we've gone down. And I will ask the student to summarize the argument. Please explain to me now, with this claim that I've written down, using this idea that you've done here, explain to me why my claim is true. And I will hope that the student will say something like, well, when we distribute 5 dots amongst this larger box, that's equivalent to distributing 5 dots amongst these 4 smaller boxes. There must always exist a smaller box with 2 or more dots in. And because the most you can ever separate 2 dots in the same small square is root 2, that means I'll always find a pair of dots that are within root 2 of one another. That's the kind of succinct argument I would like. So you see, it wasn't enough for us to just kind of, I couldn't just handhold you through the whole thing and then get us to the end point. What I wanted then is for you to effectively give a recap of the logical arguments that we'd been through. So there you go. That was now what I'd said, the new information. And somebody very clever, I'm sorry, I didn't catch your name. I think I'd seen this this is called the pigeonhole principle. This idea of if I have, it's called the pigeonhole principle because we usually phrase it in terms of pigeons. If you have n pigeonholes, but n plus 1 pigeons, then there's always going to be a pigeonhole with 2 or more pigeons in it. Here, the pigeonholes were these 4 boxes. And our pigeons were the 5 dots. Excuse me. So effectively, that's the principle you've been introduced to. That was the new idea. And remember I said one of the things I like to see in an interview is you take on a new idea and then use it in a new scenario. So let's do exactly that. So I then get out another piece of paper, one I prepared earlier, and I say, right, similar looking problem, right? Here we've got an equilateral triangle of size 2, or width 2. And I say, right, if there are 5 dots within this equilateral triangle, my claim is that I can always find 2 of them that are a distance of within x of each other. And my question is, what's the smallest x so that the claim remains true? So if you very quickly go back to this one, when we did this, the x here was root 2. And we knew that we couldn't make this any smaller because if someone came along and said, I think this same claim is true with a smaller number there, this configuration of dots would have been a counterexample. Because you see, the closest any 2 dots get here is root 2. So if somebody claimed that you can always find 2 dots within something that's smaller than root 2, you'd give them this configuration of dots and say false. So root 2 is the best number here. I want to know what the best number here is for 5 dots distributed amongst this equilateral triangle. And this is where I'm quite happy for silences to happen, because I want the student to have an opportunity to really think. Sometimes in an interview, it's tempting to just not really think and just panic a bit and just wait for the next hint. I'm afraid you have to engage brain. But to do that, you have to relax. You have to go, right, okay, I'm going to focus on this problem. What was the idea in the previous question? What was that kind of eureka moment that allowed us to answer this problem? Well, we used the pigeonhole principle. But what was it? Well, we took the square and split it up into 4 smaller squares of equal size. is there a similar idea that we could use here? Now, I wouldn't have told you that. That's what I'd want you to be thinking, like, can I use a similar trick? Now, you're at a huge advantage here, because if you played a lot of video games, particularly in the 80s and 90s, a particular game called Zelda, then the corresponding very good, very good. The corresponding way of splitting this triangle would be to, well, what if I do this? If I split it there, there, and there. So this is meant to be, this point here is halfway up this edge, etc. So would you agree now that this equilateral triangle of size 2 has been split up into 4 equilateral triangles, but now the edge here is of size 1? So this is starting to feel familiar, right? Because how many dots are we distributing? We're distributing 5 dots. How many places do I have to put my dots? Again, I've got 4 places. So we could use that pigeonhole principle. And that pigeonhole principle says that, look, I've got 5 dots and I've got 4 effectively pigeonholes. There's going to be at least one pigeonhole or small triangle in this case that will have 2 or more dots in. And because all the triangles are the same, it doesn't really matter which triangle would have 2 or more dots. So let's say it was this triangle. So there's going to be, the configuration is going to look just like that. There's 2 or more dots in one triangle. Then what is the maximum separation of those 2 dots? Well, if I have 2 dots in the same smaller triangle, the maximum they can be separated by is if you put them at 2 vertices. Let's say put one here and one here. And so it's always going to be the case. And of course, this distance here is 1. And so if we have 2 dots in the side one of these smaller triangles, we know that there's always going to be 2 of them that are within 1 of each other. This is just like the previous problem, just a slightly different shape. And so at the moment, we're thinking, well, maybe x equals 1. But are we really there yet? It's certainly now true that if I put x equals 1 here, then this claim is true, because this argument has effectively gone through y. I'll always be able to find 2 that are within 1 of each other. But I wanted to know what the best x was, because maybe there's some very, very clever argument out there that could demonstrate that actually, while this is true for x equals 1, an even smarter argument might say that the same statement is true, but for x being a half. Maybe if there was some clever dissection of this triangle. Well, what did we just talk about in the last one? We said that we couldn't do any better than root 2, because if somebody claimed that was a smaller number than root 2 that would work, you gave them that configuration of dots that you felt spread them out as much as possible. And so if you want to show now that x equals 1 is actually the smallest possible x that you can use, then what you can do is demonstrate some configuration where no 2 dots are any closer than 1 of each other. And so how can I maximally split dots up on this thing? Well, you do the obvious thing. You kind of put them at some vertices. Are we happy that with that configuration of dots, no 2 dots are closer than 1 of each other? So you see, these are within 1 of each other, these are within 1 of each other, 1 of each other. And so if anyone came along and said, I think you can always find 2 dots that are within a half of each other, for example, you could give them this and you could say, well, no, half doesn't work because look, these are all separated by 1. And actually any number smaller than 1, this serves as a counterexample. So what we've demonstrated actually is x equals 1 is the best possible number. So it is the best possible number to put in this slot. So if you're interested in this idea, you can have a look into the pigeonhole principle. And there are loads and loads of problems on this pigeonhole principle. And again, in the interview, I wouldn't have expected you to see the pigeonhole principle. It would be the idea that I was giving you some new information. So don't worry if you haven't seen anything like that before. I wouldn't have expected you to have seen it. Second point, we've just gone through that super quick. In the interview, it would have been more like 20 minutes. So if you haven't seen the Pigeonhole Principle before, would have been more like 20 minutes. So don't feel that that seemed to go lightning fast. It's just that we have time constraints, and so I can't go quite as slow as I would do if we were doing the real thing. Great. Well, I think that's me done, Alex. So should we go up to Q's and A's?
Yeah. Do you know if Thomas will be joining us today?
Yes, he is due to be joining us. He has confirmed, but bless him,
Just
he
confirm.
finished his exam at 5 o'clock, so he's making his
Yeah.
way over from the exam hall.
Brilliant.
Uh,
Okay. Just making sure.
Great. So, can we remind people that the method by which you can ask questions are they anonymous, Alex?
They won't be, but that should be okay. It'll be
Yep.
displayed everywhere. You can ask anonymous questions if you'd like to
Yeah.
be.
So yeah,
So
feel
just
free to
do.
do that. I should add, right? So of course, ask me any questions you want, but Alex is the best person to ask about these things because he's only recently finished his degree, so he's been much closer to it than I was. Am I able to get rid of my phone thing? I could just leave. Can't I? There we go. Great. So I think. So if a person has seen the pigeonhole, so the question there was, would the pigeonhole principle question be particularly illustrative of how good a candidate was? Is it not a bit too simple? So of course, if you've seen the pigeonhole principle before, these problems are kind of like, I can see what to do. Because if you've done 10 pigeonhole principle questions, these ideas come to you almost immediately. But the key here is using this question where the pigeonhole principle was not existing knowledge in the candidate's head. If it was, then of course, well done for the candidate for knowing that and probably racing through the question. But I wouldn't have got much good data from that, so we probably wouldn't have spent much time on the problem. So that's a really good question. I want to see how you deal with new ideas. So yeah, very good. So Alex, I guess that one's for you.
Yeah. So why did I choose Homerton in particular? So like I was talking at the start, the main teaching is fairly standardized across the mathematics in mathematics across the colleges. So I knew that the I would get the same course going to any other college, and I particularly chose Homerton because it was a little bit further out from the centre. It's also very close to the train station, meaning that I could get home fairly easily if I wanted to go when I was going back over the terms. And importantly, like I mentioned at the start, it has brilliant football pitches. We are the only college with a AstroTurf football pitch, and I love sport, so it was brilliant for me. I would say that for Homerton, it's pretty advisable to have a bike. We also have plenty of links with the U bus, which is the university bus, goes through and passes quite a few of the faculties, and there is plenty of other links and other bus routes that you can take as well.
Thomas is
Yes.
just so Thomas is an existing 1B student. In fact, he's been incredibly generous with his time because he's just had to rush over from a 1B mathematics exam. So thank you very much, Thomas. Yeah, we've just had a question that you might like to answer as well. It was effectively why did you choose Homerton when you applied?
Um, well, I chose Homerton because I came here in June or July on the open day, and I really felt it was a very welcoming college and was well received there, and I really liked college on when I first saw it. I was also given advice by people in the school that Homerton is a good college to apply to instead of maybe John's or Trinity if you're just want to get into Cambridge, not necessarily to get into the most prestigious college. Um, if that makes sense. So if you're a borderline candidate, you're more likely to get in at Homerton than you would be at a um, slightly more prestigious college.
So Thomas, you've done yourself a great disservice there. That's not the case. So we actually have what the pool. So if you haven't heard of the pool before, anyone listening, the pool is this great kind of normalizing factor. What happens is any given college in any given year has too many good candidates, and sometimes different colleges in a given year might not have enough good candidates. And so what we have is called this pool, where the candidates where there wasn't quite room for them, but they should definitely be students at Cambridge, they overspill into the pool. So the idea is with this pool factor that if you apply and you're of the right Cambridge standard, you should be getting the offer. And Thomas was certainly of the Cambridge standard. Otherwise, we wouldn't have. There's no such thing as borderline. We either think you'll do well or not. I think there is another question that's just come through. Do we always try to ask questions with topics the student haven't seen before? It'll be a whole mix. So sometimes, I'd like to see you just do some calculus. If you tell me you know how to integrate things, maybe we'll do a little problem on integration by parts or integration by substitution. But it is nice to have a question on material that you're at least slightly unfamiliar with, because I want to see how you deal with those new ideas. So it's not the only thing about the interview, but it is a part of it. So that was from Anonymous. It was great. Anelia, when it comes to Fermat's principle and how light takes the least amount of time, how does the photon know that? What an absolutely fantastic question. That is a question for metaphysicists and not for me. The experimentalist says this is what happens. The philosopher might talk about the consciousness of the photon. The mathematician solves variational problems and gives you some parabolic light trajectory. So I'm perfectly honest, I don't know. I'm sure there's kind of very strange quantum mechanical things there, because you're right. It's not even a local thing. If you try and minimize the time of flight locally, as in just with knowledge of let's say the temperature of air around you, that's not necessarily a global solution. You might have to go into a cold patch first to then get into a really, really hot patch. So it's a wonderful question, but I'm afraid I'm not qualified to answer that one. That's metaphysics from my perspective. I've just lost one.
That was the previous question, so you can
right,
mark them as answered.
So bad EPQ grades. So remind me, Alex, what's the EPQ grades?
The EPQ is a extended project qualification, which is part of like the A-level course that you can take.
Oh, I remember. Yeah, they've changed that. Yeah, okay, I do. Yeah. So our main issue is we want to see that you're estimated very good grades in your maths and further maths A-levels. If your teachers say, I expect so and so to get a B at further maths, then that's not great, because we'll need you to get an A*, but we'd also need you to do STEP as well. So we want to see that you've got kind of promising predictions for your maths and further maths A-levels, and also for what that third one is. Although we don't ask for an A* in that one, that's usually just an A. But no, I don't think a bad EPQ grade would be at all detrimental to any application. What makes a mathematics personal statement stand out? It's a great question. Do you know what? Honesty, it goes an awfully long way. If you have genuinely enjoyed learning about a given topic, then tell us about it, and that's interesting for us to read about. But don't try and make out you've been looking into, I don't know, quantum field theory on curved spacetimes or something, because I know you want to sound impressive, but there is a certain line beyond which it's meaningless for you to say certain statements. There was a book that was published about 15 years ago by a wonderful mathematician called Roger Penrose, and the aim of this book was to go from Pythagoras' theorem to supergravity. It's pretty much impossible, right? The book, if you haven't got a degree in maths, you can't really read the book. The first year that book was published, we had about 10 students said they read it from cover to cover, and they understood everything. And I thought, brilliant, because I thought the section on twistor bundles was actually quite complicated. Explain to me what a twistor bundle is. Of course, not being serious there, but there's no point making out that you know more than you do, because it's transparent. So do demonstrate genuine curiosity, genuine interest in the subject, but don't try and make out you know more than you do, because it usually it's transparent. Good question. How should you prepare for interviews? So what we kind of do in interviews, we don't do things like, I don't know, divide 101 by 12 to 13 decimal places, right? But we're not really interested in long division or, integrating polynomials. We want to do problems. One of the issues we have with the A levels is you're given exercises more so than problems. So I would look further afield for the kind of problems that you want to try and tackle. Is this wonderful book, Advanced Problems in Mathematics by Stephen Seeklos. God rest him, he's not around anymore. But he produced this wonderful free book. It's completely free to download. It's got all these problems. He then has a discussion of the problem, and then he has a full worked solution. So if you want a source of difficult, challenging problems where you've actually got someone who's willing to discuss them in paper format, that's a great place to go. So maybe we can write. Is there a link to it, Alex?
Yeah, I can pop it in.
Brilliant. We'll pop that link in. That's a great place. Also, if you like things like, look for puzzles. Puzzles, I think, are more fun than exercises. So, Thomas, do you have any input on the kind of things that you would have found helpful?
Yeah, I was just about to say, I'm sure many of you will be aware of there's something called the TBO problem solving booklet, which has about 150 like genuine problems rather than textbook questions, because the idea of preparing for an interview is not doing a textbook A-level question. It's using the same knowledge, but constructing it in a way that makes you think and put pieces together. So if you're aware of that, it's called the TBO problem solving booklet. It's, I'm sure, very easy to find online. And I would also say being in a place where you're actually talking about maths out loud and explaining your thought process in your room rather than just writing it down is an important skill, because you have to communicate the way you're thinking and your thought processes with people who are academics so that they actually understand how you think. And doing that well is a really important part of the interview.
Excellent. Well, we were speaking of the same thing before, actually, Thomas. It's a great point. Yeah. So this is communicating to a third party how your solution, how your idea works. So what was so that was how to prepare for interviews.
I would just, while we're on the
sorry, Alex.
I would also recommend well, first of all, TMUA prep will get you pretty up to date for problem solving questions, but also the UK Maths Challenge. There is a whole database, and that's how I prepared personally for the interviews. So just before we go on.
Oh, great point. I forgot about that. So what tends to distinguish successful Cambridge maths applicants? It's not one thing. I mean, if it were that the interviews would be much shorter, I just figure out whether or not you had this one thing within 10 minutes and that would be it. It's a whole range of things. So, for example, one of the big shocks that students have when they come to Cambridge, students often, when they're doing maths, they've breezed through their A levels. You give them an A level problem, they sit there and do it, and then move on to the next A level problem, sit there and do it. But when we give you problems at Cambridge, often you can read them and you've got no idea what to do. And you might have to think and not be necessarily writing anything down. You might be just thinking for half an hour about what's this first step? What ideas can I come up with? Can I scribble a couple of ideas down? Maybe can I look for a pattern here? What if I tried induction on this? That's a big shock to the system. And so, as I mentioned before, I really want to see enthusiasm for the subject. Because if you're confronted with that and you're actually not that into the mathematics, some people just go, oh, well, I'm not going to bother. If I couldn't do it within 5 minutes, I'm probably never going to be able to do it. And actually, that's not the case. But you have to be able to work hard at things. And obviously, we want to see that you've got some mathematical flair. The thing I mentioned before about taking on new knowledge, effectively, what we did there was I've introduced you to the idea of the pigeonhole principle. Can you apply that new idea? So they're things that tend to distinguish successful applicants. Things that don't, perhaps if I tell you things that don't go down well, if you're very, very quiet, it's difficult for us to give you much credit, because you might be thinking brilliant things, but if you don't communicate those things to us, there's nothing we can do about it. So my advice is in the interview, if you're given a problem and the answer doesn't jump out at you, it very rarely jumps out at you. You should talk about what you're thinking. Explain to me your thought process. You don't have to give me the answer and the perfect argument. You can just go through your kind of, in your mind's eye, what are you thinking when you think of this problem? So that's very, very important. If you don't do that, it's very difficult for us to get an idea of how your mathematical mind works. Okay, for a student passionate about chemistry and also mathematics, can you tell us if it's the same style of interview if the student ever chooses chemistry? Well, I don't want to speak for the kind of the fellows in chemistry at the college, but I would imagine it would be similar in the sense that it would be a technical interview. You might be asked some things on inorganic chemistry, some things about organic chemistry, benzene rings, whatever the things that they talk about there, but that kind of stuff. But it wouldn't be, again, I don't want to speak for the chemistry fellows, but it's not going to be a chat about your favorite area of chemistry. There will be some quantitative questions involved because they want to figure out whether or not you'd enjoy the chemistry part of the natural sciences triples. Are the professors there too during the open days? Yes. So we have to be careful. There are different types of open day. So the university centrally organises a mathematics open day. It does two of them. And then the college has the choice on one of the mornings. They're usually about a week apart, aren't they, Alex? Right?
So we actually have upcoming Cambridge Open Days, which will be a university-wide, and I believe the faculty will be open on that one, on those ones.
Yep. Yeah, well, the faculty is always, you can always go along. But there was the one I was thinking of where it's the maths faculty in particular put on an open day, but the college have the ability
One
to
at the
put on
same
something
time.
in the morning.
Yes. So unfortunately, that was about a month ago. We had two of them a week apart. But I believe there is the Cambridge University wide open day, which will be on the 9th, the 10th of July. And excitingly, for more of kind of the STEM students and definitely the maths students, we'll be running the STEM Escape Adventure. I'll drop a link in the chat shortly, but this is a escape game that's been designed by Paul Elliott, and it's meant to encompass kind of all subjects in STEM, and it's meant to kind of develop your reasoning skills and your problem solving skills for all sorts of interviews. If you want to go into natural sciences, chemistry, maths, you would definitely want to have a go at this if you do, if you are going to come to the open day. And important and amazingly, it will stay open until 6:30 as well. So after the kind of all the other colleges closed down, we'll still be open doing this as well. So please do come along because I think it'll be really interesting for you guys.
Oh, fantastic. Which area of mathematics do you think most students struggle with? Oh, that's a tricky one because I guess it depends on personal taste. You know, some people love statistics, some people love mechanics, some people love calculus, proof by induction, and also people do slightly different syllabi. So it might be the case that one person wasn't exposed to a certain bit of mathematics that another person had been. We don't tend to. When we ask questions, we either try and introduce a new idea, so it's a kind of level playing field, or we'll ask maths questions that depend on kind of core knowledge. So everyone who's doing a maths A level will do some calculus. You'll solve a differential equation at some point. You'll sketch a few graphs and things. So when we ask questions about specific bits of A level knowledge, we try to make sure that it's definitely something that everyone has covered and it's not something on the fringes. What was the next one? How important is your personal statement in your application and what can make it stand out? Again, for me, it's enthusiasm. So it's one thing to say, oh, I really like maths and I'd like to do maths at university. Okay, granted. But have you actually done anything to demonstrate that statement is true? You know, have you read a couple of extra books? Have you been working on Stephen Seacloss's problem book? Have you looked into some of the first year courses that you might end up studying? You don't have to know anything about them, but you might say, well, I've seen there's a course on groups, and apparently I read somewhere that groups are a bit like symmetries. And is that true? You get brilliant. I'm not asking you to be a specialist in group theory. It just means that you've independently looked up some of the mathematics you might learn about. You haven't tried to be an expert in it, but clearly you're looking beyond the A-level syllabus because you find the stuff interesting. For me, that's great. That really stands out. But to the other end of that, and I said this before, don't try and make out you know stuff that you don't, because it's not worth it. And also, personal statement is not the be all and end all. So plenty of people write a fairly middling personal statement, and they still get the offer. So it's not a make or break thing, but it does pique my interest. If you've said something interesting there, it's like, oh, I'm looking forward to interviewing this student. It's the person that said about Gauss's theorem egregium and eating pizza. That sounds great. Maybe we can chat about that. So what was that? I've lost my track. Sorry, Alex.
I have just dropped a link to the faculty webpage, which has a reading list. So if you'd like to have a look and indulge some of the books in there, that would be
brilliant. Which one am I down to? I was just trying to, because it's scrolled up slightly.
Would we do the ones that students have struggled with?
No, is it which books, lectures, and resources would you recommend?
Yes.
Right. So I would, if you want to go beyond the curriculum, as in like learning some stuff that's in let's say first year of maths, I'm not saying don't do that, but let's just be pragmatic. You've got some exams coming up, especially the step exams. And what I'd prefer is you pass those step exams. So get really, really good at the A-level stuff, practice the step stuff, and then perhaps after your step exams, then maybe look into the further material. If you want some reading lists, if you go on the faculty website, you can find something called the schedules, the mathematical schedules. And Alex, is it possible to put a link for that in there? I haven't. Basically, the schedules contain effectively a syllabus for every single lecture course in the mathematical tripos. And for each course, it gives a brief reading list. And so if there was an area of mathematics that you were interested in, let's say I mentioned before, group theory, maybe you want to learn more about groups, then in the schedules that we'll give a link to, oh, brilliant, Alex just found it, you scroll down to where you find the 1A groups course, you might read the description of the course, and then have a look at the books that are recommended. So that's a good way to do it. But please, my recommendation is try and practice the A-level stuff and the step papers first, because if you don't manage the step exams, or at least do sufficiently well, it might be a shot to nothing. But very good question. So Thomas, that's a good one. So literature, other supercurriculars, recommend a few. So I guess it's the same thing. If you look in those schedules, there's bags of knowledge. What I wouldn't try and do is don't say, oh, it looks like I think I'll really like analysis. I like the probability course, and I'll also like differential equations. So let's try and learn a bit of that. That's way too much. But you might say to yourself, I'm just going to dip my toe into, I don't know, vectors and matrices. That's one of the courses. And you could try and kind of build up your knowledge on that one thing. But I'd be reluctant to recommend that you go and try and start your degree slightly early, because you need to have a bit of a break. And believe me, when you come to Cambridge, you will be very, very busy. So it's good to enjoy the summer before you come up. Don't get me wrong, you'll have fun, because you'll be enjoying the maths, but it is hard work. So that's important to remember. Well, thank you for that question. Any tips for preparing for the test evaluation? The test evaluation is the beginning of the academic year. I'm afraid we may get topics we've not covered at all yet. So are we talking about the written test that happened before the interviews, or are we talking about the kind of like interview questions? Maybe if the person who wrote it 6.06, if you ask that question again and just clarify, and I'll come back to you.
I think it's the bottom. So before the interview questions, so the TMUA. The TMUA, I think, is based off first year A-level content, so exclusively A-level maths, not further maths content, and actually is just meant to be kind of like vamped up problem-solving GCSE questions as well. So hopefully content should be fine. If you go to the TMUA website, it will tell you what is tested as well, to make sure that you have kind of independently studied any extra stuff that your school might not offer before you apply.
Excellent. Thanks for that. So how does a college decide which candidates to pick and which candidate go to the winter pool? Well, we try, if I let you in here, what we try and do is try to evaluate you on each question. So if somebody rolled through a question really quickly, and it looked like they hadn't seen this material before, but they did fantastically well, they communicated their ideas, we might say, wow, that was like a 5-star answer to that problem. And we go through all of them, and we try to look, how many 5-star, 2-star, whatever they are, and we try to effectively gauge how well each interview went. So there's no perfect metric. And we also have different interviewers. So sometimes one interviewer's version of events might be slightly different to another. So we talk a lot about the individual interviews at the end of every day to figure out, who's in our offer pile and perhaps who isn't. So when it comes to who do we put in the winter pool, we start saying, look, these candidates might have been just on the edge. If only we could take on 12 students, but we've only got space for 10. It's like, okay, perhaps if we look at, let's say I said, well, I thought that person there got 2 5-star questions and this person only got 1 5-star question, I might say, well, okay, if we've got to make that cut, then it might be on that decision. But there's no hard and fast rule. We're just trying to figure out how many people we can get in, and if there is overspill, we know that hopefully they'll be taken up in the winter pool, or of course the summer pool. The summer pool also happens after the exam results have come out, just in case you've just missed your results, and the college doesn't have room, but you can be put in the pool because there might be a college that has spare capacity. So for for US-based students, which 5 APs are preferred, if any? The most mathematical. What the US syllabus is very different to the A-level syllabus, and what we tend to do is try to look very carefully at what subjects have been covered and ask interview questions accordingly. This does actually happen with quite a few international students. I mean, in Eastern Europe, for example, the syllabus on their high school exams is wildly different to A-levels. So when we have cases like this, we pay specific attention to what subjects have been covered, and then we go ahead and ask questions based on that. So the interviews, we are willing to be flexible where some people have perhaps not covered as much stuff as others.
I will say,
oh, sorry, go on.
Just as a necessity for APs, because we require further maths, you will need to do Calculus BC, which is a course that we require for further maths. AP.
So will this recording be posted anyway? Yes, I believe so. So Alex, I think, are you going to send out the YouTube link at some later date?
Yes, so just look out for it. It should be on our website as well. With this, and you can see this.
Yeah. Thank you. Brilliant. Also, how many of the programs with 10 students? Approximately how many go to 10 students? I tell you, the variance there is quite. So the question here was approximately of the 10 students that enter into Homerton as undergraduates, approximately how many carry on to do part 3? So I perhaps should have explained this. Part 3, paradoxically, is the 4th year of the mathematical tripos, and it's very advanced. So there are certain academic prerequisites to be able to go in, and also some people that have those prerequisites choose not to go into it because they don't want to specialize anymore. They might want to go on into the world of work. I'd say on average 3 or 4, but the variance is quite high. We've had 7 in the past, and also we've had just 1 in the past, and often that's because the students just don't fancy doing any more maths. They've already got a job lined up, and so they're quite happy with their undergrad degree. But yes, it's personal taste, so it's it does change quite a bit. But I'd say on average about 4. Does the interview involve discussing the type of maths you like discussing in the personal statement? I mean, it can do. There might be if I can see there's a person has mentioned a particular area of maths, and I happen to know there's a good puzzle that we could do involving that area of maths. Then if there's time at the end and we've already gone through some of the more standard problems, then yes, I might bring that up so we can have a discussion. So the next question is about open days. Did we find that the link, Alex, the faculty open day link? Was that one of the ones that you posted? Sorry, I haven't got my browser open.
It should be there if you go to the faculty website. They'll have the dates.
So you get to www.maths.cam.ac.uk. The open day should be listed on that website. Oh, sorry. Do you mean other faculties, not just perhaps is it the other faculties? I'm guessing again on the relevant faculty website. If you look for chemistry faculty, University of Cambridge, they will have a similar website to the mathematics ones, and they'll be able to tell you about those open days, because they don't necessarily happen all on the same day, because otherwise Cambridge will get too busy. Would you recommend that we read completely outside the A-level syllabus or extension of topics that were covered during those studies for? I don't think there's a need to read completely outside the A-level syllabus. I don't think there's any problem topping up some ideas. So, for example, if you've seen the idea of a matrix, vector in your A-levels, but you haven't seen things like eigenvalues and eigenvectors, well, you could top up your knowledge slightly, just extending your A-level knowledge just a bit. But that's a very different thing to going off and say, right, I'm going to learn about what a topological space is. So topping up this stage, I think, is good. But trying to kind of master completely new things is a bridge too far. How's the psychological state of the student, and what is the approximate dropout rate? The dropout rate is very, very low. So the university has a policy whereby if you fail your exams, in 1A or 1B or certainly part 2, then if you don't have a very good reason for failing them, then you're asked to leave the university. It's a prerequisite from going from, let's say, 1A to 1B and from 1B to part 2 to pass your exams. And typically, of the around 250 students we have, there might be a handful, maybe 3 or 4, that don't go through. In terms of Homerton, I think one student over the past 5 years, or it's probably more than that. 7 years. I think one student over the past 7 years. I'd have to double check that, but they're not big numbers at all. The vast majority of students make it through. And the psychological state, I think one of the things that's a good and serious question. One of the things that the students struggle with initially is going from in school, give me a page full of exercises and I'll just jump through them, to a university. Again, I've mentioned before this idea of you've given me a list of problems and I just don't know where to start. It's this idea of I'm thinking, but I'm not necessarily writing down. That is the biggest, in my experience, psychological barrier for a lot of students, to think that if they're not writing something down, then they're not actually doing maths. And actually, that's not how it works. Maths is often about spotting patterns, trying ideas. Often you try to do a question 3 different ways and they don't work. But the failure in those 3 tries gives you a hint on what might be the successful route. So getting over that new way of studying maths is tough, but the vast majority of students have no problem doing it. Are certain colleges more difficult to get into than others? So again, this comes back to the pool thing. So you can look at the statistics of application rates on the colleges every year. And what you'll find is they're incredibly dynamic. They change from year to year. Because even when people, let's say I saw a college that had very, very few applications in a given year, and I was trying to play the system, and I thought, well, I'll apply to that college because it'll increase my chances of getting in. Well, you and about 60 other people had the same idea. And you suddenly realize the number of applications for that college went boom, having just been down here for the previous year. So you get lots of tallying around. And so the idea with the pool system is that we want the people who can get through successfully the Cambridge degree, we want to make sure via the pool system they end up at some college. And it's very, very effective and it's worked for many, many years. Can international students take STEP as well, or is there equivalent to Eastern? Oh yes, absolutely. You can take STEP anywhere. So yes, it's STEP for Eastern European students as well. And we've had lots and lots of very successful Eastern European students at Homerton. They've all managed the STEP. Have to remember that your syllabus will be slightly different to the syllabus that the STEP exams are based on. So it'll be important to kind of go through the things that are covered in STEP, because you might need to top up your knowledge in one place or another. So are there mature students at Homerton as well? I know the mature colleges, but yeah, there's lots and lots of mature students. We have lots of graduate students. But do you mean mature students studying an undergraduate tripos? I guess that's the... So we've had applications from mature students before. There's certainly nothing wrong with that. Usually, the mature students prefer to go to a college where they're surrounded by mature students. But if you were to come to college as a mature student, then there are already lots and lots of graduate students at the college who would be a similar age. We've got a huge actual spectrum of ages in the college. So yes, absolutely, we do. And how do you best prepare for STEP? Ooh, the ultimate question. Start with step 1, past papers, and gradually work way up to step 3. You know what? That's a great way. Of course, we don't have step 1 anymore, but whoever gave you that advice is a great bit of advice, because step 1 was meant to be kind of like the lowest rung of the ladder. So if you can cut your teeth on that first bit and then start building up, I think that's a great idea. And I would also stress again that Stephen Seacloss booklet. He actually I think he ranks the problems, right? He gives it like, is this a 3 hard or a 2 hard or a 1 hard? So Thomas, here you go. So Thomas is going to tell me whether I'm wrong.
Oh, I wasn't going to tell you where you're wrong in any sense. I was going to say an additional resource specifically for STEP once, because it's also good to start thinking about STEP before the interview. I wouldn't say start from STEP from January of when you get your offer. I would say think about STEP now. It's a very, very hard exam. There at Cambridge kindly offers a free resource called the STEP Support Program with 25 foundation modules. My best advice would be try and do those 25 over summer. That's averaging one exercise, which may take 2 or 3 hours every other day, say. And if you do that, you'll be in really good stead. And then start thinking about past papers throughout year 13. I did about 20 years of past papers. They gradually get harder. So if you start from the earlier ones, you'll be well prepared, because the more recent ones I find are harder. That would be how I prepared and how I think would be a good way to prepare. But I'm open to other thoughts.
So Thomas is incredibly hard worker. So that is a lot of past papers. I don't expect many people have done that many past papers, but he is absolutely right. These things get easier the more you expose yourself to them. So initially, you'll see your first step 1 problem. You think, my word, that's the hardest thing ever. But you will have such a moment of elation when you solve your first step problem. And that will make you do the next step problem and the next and the next. In fact, it's those kind of incremental bounces that help mathematicians get through the day, because most of the time we're not proving big theorems. We're trying to, but the answer doesn't come to us. But then eventually, when we do prove our big theorem, that elation convinces us that we should probably try and prove another one. So it's all about that incremental step. So yeah, great advice from Thomas. Do we only give out 10 offers, or would you give out more, only expecting 10 to meet? Yes. So we do give out more offers. We typically give out around, in the past, around 20 offers. And we aim to take on 10 students. We found that, so there is a drop off after step. As Thomas rightly said, it is a hard exam. But yes, so we typically give around 20 offers. I'm coming from a European school in the EU. I don't know what STEP is. I'm just going to Google it, but maybe you can complete. Yes, they're called 6th term examination papers, and they're effectively more difficult maths problems based on the kind of maths that you've seen in school. I mean, the STEP exam is actually based on what was in schools in Britain, in the maths classes in Britain. But you can look up what's in the syllabus, and you've got loads of resources online. You can get all these past papers, probably going back to, I don't know, the 1980s. So there's loads and loads of stuff to look at. So just make sure, if you look over what STEP covers, just look at the syllabus of your maths high school work and make sure that there's sufficient overlap. You want to make sure that there aren't huge gaps in your knowledge, because if there are, it's not a problem, but you just need to fill them before the exams start and you start revising. Right. I think we are done.
Yeah.
So thank you very, very much for coming along. It's been great fun. I always enjoy these things. I like getting the difficult questions that I struggle to answer. That photon question was sublime. That was an excellent question. These are the kind of wonderful conversations we have at university. So I hope to meet an awful lot of you one day. Keep working very hard. And as Thomas said very wisely, on the step front, practice makes perfect. Keep on getting at those past papers and it'll make your life much easier. Alex, did you want to finish?
That's perfect. Thank you very much, Anthony, for coming along, and thank you very much, Thomas, for helping out with the Q&A today. Wishing you all the best everybody for your admissions. Goodbye.